Welcome back. Again, I encourage you to ask questions. You guys are asking a lot of questions. That's very good for today. And not this. And you are just 10 more questions away from me doing handout. There's a lot of other things I can do. So please be motivated and ask as many questions as you can during the lecture. So we have our f equals ma, but for a system. We don't need to choose any specific thing to be a system. I can choose me and Hannah over there and define this as a system. The total external force acting on us will be the mass of us times the acceleration of our center of mass, which is not so useful because the center of mass is somewhere between us, and I mean, knowing how that point moves doesn't really help us understand anything. But if we choose the center of mass of a solid, then the motion of the center of mass is basically the motion of that solid. Can you guys see this? So, if I throw this into the air, don't tell that guy. Okay, so you see, they are spinning, but overall this thing seems to be doing something like a projectile motion as a whole. But if you look at the individual motion of each ball, the trajectory of this ball is the blue line. The trajectory of this red ball is the red line. The red ball is heavier, so you can see the center of mass, which is represented by the dotted line, is closer to the red ball. If you look at just the motion of one particle, the motion is like crazy. There's no way I ask you to compute this motion. You don't even know what its function is. It's not even a function. You cannot derive a trajectory for the red line or the blue line. But if you look at just the motion of a center of mass, which is the dotted line, you see it is just like projectile motion, as you learned before. This is the power of center of mass and that equation. When we look at these two balls as a system, the external force is just the gravity which comes from the Earth, and it is outside the system. So external force is just the mass, it's just the gravity on the first ball and the gravity on the second ball. That is our total external force. When you look at the force that the rod exerts on the ball, those are internal forces because the rod is also a part of our system. We treat this rod as having negligible mass, so it doesn't have gravity on it. But the interaction between the rod and the ball, and the rod between the rod and the other ball, are internal forces, and we do not need to consider them in this equation because this equation only cares about external forces. So external forces acting on this system is just the sum of gravity on the balls. Now, this is just a m1 plus m2 times g because g is the same, so you can take them out of the parentheses. And according to that formula, this should be the total mass times the acceleration of center of mass. So you see, total mass is m1 plus m2. So they cancel, and you get that the acceleration for the center of mass is just a constant g, just like projectile motion. So that's why when you look at the trajectory of this center of mass, it is a projectile motion because it is, and it is easy. That's the power of this equation and why we work so hard on it. This works for any system because we are just choosing a bunch of particles to be our system. And if you choose quantity, you can analyze any microscopic object easily. Okay? So that's why we learn this. Now, an important thing about center of mass is the center of mass frame. According to the name, if I am in the center of mass frame, so if I am in the center of mass frame, where is the center of mass?
Right in the middle.
At the origin, yes. So that's the definition of center of mass frame. Why do I look at this frame? Because when I look at a system and there's nothing else but the system, the external force acting on the system is 0, then acceleration of the center of mass will be 0. Then it means that the center of mass frame is an inertial reference frame. So when you are analyzing a problem, you don't know which frame to choose, and you are not sure if you choose a frame that is an inertial frame or not. Usually, you can look at if there's any external force on your system. If there's no, then the center of mass frame will be a perfectly good inertial reference frame to work on your system. The example I'm going to do is, again, the sun Earth orbit. This time, let's call it MB and MA. When we do the sun-Earth orbit, we say the sun is super heavy, so we can approximate the sun's acceleration as 0, and the sun's frame is an inertial reference frame. Now, if I'm looking at the orbit between two planets, they will have comparable mass. The acceleration will both be significant, and I cannot just say one of the frames is inertial or not. It's inertial or not. But if there's no other stars around the planets are just orbiting with each other, then I can choose that to be my system, and the center of mass of that system will have 0 acceleration. Because if there's no other stars around, there's no other external force acting on them. The gravity between them is internal force. It comes from inside the system. There's no force coming from outside the system, and the center of mass will have 0 acceleration. So the center of mass frame will be a perfect international reference frame for us to work on the problem. So let's say the blue one is orbiting with a smaller circle around the center of mass. The B. And MA is orbiting around a bigger circle. Let's say this is the speed A, this is the speed B. Now, if I say MB is closer to the center of mass, which one is heavier, MB or MA? MB, good job, good. Okay, so now, I'm not actually going to solve this because it's kind of complicated, and you don't even know how to solve it. If you're interested, I have all the steps in the textbook. I'm just going to point out some important thing when we're doing this problem in a center of mass frame. So first thing is that the acceleration of the particle, which will be the center, which will be the circular motion acceleration. Let's call this Ra, the distance of MA to the center of mass. The acceleration on MA will be its own speed squared divided by Ra. So it's not going to be the distance between MA and B, but the distance to the center of its circular motion. When we say the mass of the sun is super big, the distance is just the same as R, but now it's different. You need to look at the distance to the center of mass for this R instead of the entire distance between them. Same for MB. Yeah, Pablo?
Sorry, why do we square velocity again for VA?
So the acceleration for circular motion is v squared over R.
Okay.
So I need v squared. Good question. You don't need to memorize it because if I ask you to do anything like this, I'll give you V square over R. I'll give you a formula.
Oh, thank you.
But you do need to know how to derive it if I ask you to derive it in exam. So that's one thing. Another thing is that when you compute the gravity between them, gravity is not related to the distance to the center. It's the distance actually between the two particles. So when you do the gravity between them, you have G and M, but the distance down here should be the actual distance between them. So let's call this RB. RB is the distance of the B of the sum to the center, and you need to add them and square them. That's the difference when you are doing this problem without taking approximation. So you do need to know that how to use the formula because my hope is if you know how to derive it, you'll know how to use it because you know exactly what every term means. This is the radius of the circular motion, so you need to use RA. But this is the distance between particles, so you need to use RA plus RB. Now, after some blah blah blah, which you don't need to know how to do, but if you're interested, you can go check it out. You will get something very similar to Kepler's third law. At the end, you will get a factor of 1 MA over MB squared 1, and then the period square again is going to be period square over radius cube, and this constant here is the same, but this is no longer a constant of the mass of the Earth. Previously, we say if the sun is super heavy, the mass of the Earth will not affect the period of its orbit and the radius. Now you see there's a factor of MA here. So when the mass is comparable, you don't have Kepler's third law. This is not a constant of MA. This is the mass of the Earth itself will affect the ratio between the period and the radius of orbit. But if the sun do have super big mass compared to Earth, you see that the MA over MB